Hello, in this video we're going to talk about second order partial derivatives, and the notation you'll see to begin with looks like a partial derivative with respect to x inside the parentheses, and then outside the parentheses we've got another partial derivative with respect to x. And so what this tells us to do, working inside the parentheses first, it says find f sub x, find the partial derivative with respect to x, and then with that result compute the partial derivative with respect to x again. So let's take a look at an example. We've got f of xy equals x cubed plus x squared y cubed minus sine y. And the first thing we need to do is find the partial derivative with respect to x. So that would be 3x squared plus 2x y cubed minus 0. Next, we need to do the partial derivative of the partial derivative. So the first term we get 6x, next we get 2y cubed. And that is our second order partial derivative with respect to x. So the notation you'll see, well, we started off with this parentheses notation. So inside the parentheses there's a partial derivative, and then on the outside there's another partial derivative, and so you end up doing two partial derivatives, both with respect to x. So you'll see the subscript notation f sub xx. But there's other types of notation you can also see for the second order partial derivative. For example, the curly d notation, the partial derivative with respect to x of the partial derivative with f with respect to x. And lastly, you might see the curly d notation with these 2's. It looks like it's almost curly d to the power of 2, and that's just a second order derivative of f with respect to x. So that's another way of expressing the second order partial derivative of f with respect to x. Now we can also do the partial derivative of f with respect to y, and we can do that 2 times and get a second order partial derivative of f with respect to y. So let's look at an example. We'll use the same function f of xy equals x cubed plus x squared y cubed minus sine y. So first we compute the partial derivative with respect to y, and that would be 3x squared y squared minus cosine y. Next, we need to take that result and do another partial derivative with respect to y. So that would be 6x squared y plus sine y. Remember, the derivative of cosine is negative, and we had a negative, so negative negative gives us the positive sine y. So this is the second order partial derivative with respect to y. And you might be wondering, well, can we mix it up? Can we do partial derivative with respect to x and then with respect to y, or the other way around? And we will get to that in a minute. I'd like to finish the notation here. So we've got the second order partial derivative with respect to y, and the notation for that very much mirrors what we saw for the second order partial derivative with respect to x. Okay, so let's take a look at the mixed partial derivatives. So we can go in either order. We can first do the partial with respect to x and then the partial with respect to y, or vice versa. So first of all, let's look at the partial derivative with respect to x and then computing the partial derivative with respect to y. So the notation for that looks like f sub xy, and that denotes that you do the partial with respect to x first and then you do the partial with respect to y. The other sort of notation you could see is the partial derivative of f with respect to x, compute that result in the parentheses, and then when you got that answer, hit it with the partial derivative with respect to y. In terms of this curly d notation, because there's this inside out working, reading that denominator from left to right, it looks like a curly dy dx. So you just have to know if you're in the curly d notation or the subscript notation, the order's a little bit different there. So similarly, you could do the partial derivative with respect to y and then x. So that looks like f sub yx. In other words, that's doing the partial derivative of f with respect to y and then hitting it with respect to x. Now, in general, these are not the same. In some cases they are, but not always. And so you really do need to be careful about the order in which you're working. Chloros Theorem tells us when are the mixed partial derivatives equal. Okay, so here's what Chloros Theorem says. It says suppose f is defined on a disk D that contains the point AB. If the mixed partial derivatives are both continuous, like you do them in both orders and they're both continuous on D, then the mixed partial derivatives are equal. In other words, it didn't matter which way you computed them. So, if you wanted to sum that up, you could say, if the mixed partials are continuous, then the mixed partials are equal. Now, obviously there's a few details to keep track of. We're talking about a point AB on a disk D, but roughly speaking, if the mixed partials are continuous, then the mixed partials are equal, and that's Chloros' theorem.